So let's do quiz 7 review of calculus 2. So the first question is, does the series converge or diverge? So we use, anytime you see a -1 to the power of something, so we use the test called the alternating series theorem. So we're using alternating series theorem. And to apply this alternating series theorem, I'll be calling it AST, abbreviation AST. To apply this one, we have to check, the three condition has to be satisfied. So first of all, let's go have the Bn term. And the Bn term is that part which doesn't have a minor, that's n squared divided by n cubed plus 1. So the first condition is that Bn should be positive. So Bn should be greater than, or should be positive. And we can see that because if you are n is starting from 1 onwards, so if you plug in the values of n, you get that this one is satisfied. So the second one, it's the function should be decreasing. So we have that Bn plus 1 is less than or equal to Bn. So we can check this one easily by finding the first derivative. So we check by first derivative. I'm calling it first derivative. And this we do that by, we call the Bn, we call it f of x. That means where I have n, I'll put an x, and I'll have x squared divided by x cubed plus 1. So the derivative here, that is first derivative, f prime of x, will be, if I have the numerator as my u of x and my denominator as v of x, I'll be using the quotient rule, which is u prime v minus v prime u divided by v squared, which will give you the derivative in the numerator is 2x. You multiply by the denominator, that's x cubed plus 1 minus the derivative in the denominator, it's 3x squared. Then you multiply by the numerator function, that's x squared. Then you divide by the square of the denominator, that's x cubed plus 1 squared. So we simplify. We have 2x to the power of 4 plus 2x minus 3x to the power of 4 divided by x cubed, I don't have to expand, plus 1 squared, because my only interest here is to see the answer in the numerator, and that becomes minus x to the power of 4 plus 2x, and that's a quadratic binomial. So it has the highest degree, it's 4, and denominator is x cubed plus 1 squared. So the fact that I'm having a minus in front of the highest power of x, that becomes, this function is a decreasing function, and you can check if you have to substitute with any value of x being equals to 2, x being equals to 3, x being equals to 4, whether this function is decreasing. So with that, we check that condition. So that condition will be now to find the limit as n tends to infinity of Bn, and we expect if it's equals to 0, that's when it converges. If it's not equals to 0, then it diverges. So we have limit as n tends to infinity, our Bn, it's n squared divided by n cubed plus 1. And as n grows, or what we get interested here, it's the behavior, the end behavior of this function. So and that one can, it's seen clearly by checking the highest power of n in the numerator divided by the highest power of n in the denominator. And this one becomes 1 over n. So, and then as n grows of 1 over n, this one goes to 0. And if the limit as n approaches infinity of the function goes to 0, and the two other conditions are satisfied, then we say that so we conclude that the series sum as n starts from 1 to infinity of minus 1 to the power of n minus 1, then multiplied by n squared, this divided by n cubed plus 1 converges. So that's the first one. So I make clear all that, and then I go to the next part. So the second question is determine whether the series below converges absolutely, converges conditionally, or diverges. And as we said in class, that all the times we see the factorial, it gives us a hint that we need to use the ratio test. So I'll write the things we need to know for the ratio test. On the ratio test, we say if limit as n approaches infinity of this ratio an plus 1 divided by absolute of an, if this one, and I'm having the conditions here, if this one equals to 1, we say the test is inconclusive, so the test fails. So we cannot use this test to test for convergence if the answer equals to 1, so the test fails. I would have started if the answer is, if the limit is greater than 1, and I mean strictly greater than 1, then this one diverges. And if the answer or the limit as n becomes big is strictly less than 1, then this one converges absolutely. And if a series converges absolutely, that means it will converge. So let's have this, our an equals to minus 3 to the power of n divided by 2n plus 1 factorials. So our an plus 1 will be equals to minus 3 to the power of n plus 1 divided by 2n, but now n becomes n. Whenever I have n, I put n plus 1, now plus 1 factorials. So this will become minus 3, let me write it in a more clear manner, divided by 2n, if I distribute to 2n, then 2n plus 2, then plus 1, it was out of the parentheses, factorials. So this is the same as minus 3 to the power of n plus 1 divided by 2n plus 3 factorials. So and now we can apply the test. So limit as n approaches infinity of an plus 1. So with absolute terms, the minus will be disappearing. So be having 3n times 3 to the power of 1, that's 3n plus 1 as the power, divided by 2n plus 1 factorials. And because I'm still dividing, I can write here this division, divide by the an, which is minus 3. So I can write 3 to the power of n because because of the absolute terms, the minus will disappear, divide by, so this one, sorry, this one is to the plus 3. Now this one is 2n plus 1 factorials. So because we continue, we have limit as n approaches infinity, 3n times 3 divided by 2n plus 3 factorials multiplied by 2n plus 1 factorials divided by 3 to the power of n. So we can cancel 3 to the power of n, and then we simplify and write it here as limit as n approaches infinity, and then we have 2n plus 1 factorials, and then observe that the denominator remaining is 2n plus 3. So we can reduce the plus here. We have 2n plus 3, 2n plus 2, and then 2n plus 1 factorials. And then 2n plus 1 and 2n plus 1 will cancel, giving us limit as n approaches infinity of 1 in the numerator divided by 2n plus 3, 2n plus 2. And as n grows, this answer will go to 0. And 0 is strictly less than 1, so this one converges absolutely. And what converges absolutely is the sequence that we were given, the series that we were given, that this sum converges absolutely. Finally, the last one, we will use the other one, because if I see that to the nth power, the test that I will use to test for convergence, it's called the root test, not the ratio test for this case. So we use the root test, and again, we say if limit as n tends to infinity of nth root of an, if this one is strictly greater than 1, let me start by less than 1, sorry. If this one is strictly less than 1, it converges absolutely. If it's greater than 1, and also including infinity, also even in the last one for the ratio test, including infinity, this diverges. And if it's equals to 1, this test will fail. So we cannot use this test to conclude if the answer equals to 1, if the ratio equals to 1. All right. So again, let's see here. So limit observe for this case, we won't use the root test for this because of the -1. So in that case, we will revert to another test. So I'll give this one as a, I'll complete this one and later, but let me show you what I wanted to give for this one. So let's use let's have the function without a minus, then we do the minus later, but not with the root test. So for the root test, let's take this one as the numerator as 1, the power of n minus that. So that's the numerator as 1. And then we do the other one with -1 in the next part. So we have limit as n approaches infinity of nth root of now this without a minus, 1 over n nth root. So this is what we did in class. So we have limit as n approaches infinity of 1 all this to the power of n. Then because it's nth root, we raise to the power of 1 over n. So this one become limit as n approaches infinity of nth root of 1 over n ln of n. The n we cancel with this n. You get 1 over n natural log of n. And with that, we can check, or we can see that as n grows bigger and bigger, 1 over n ln of n will go to 0. So that will tell you that the function converges absolutely. So let's use the one which had a minus, and let's do the test in this case. So if in this case we were given the function, which is in this case we will use alternating series theorem, and we'll have, let's use alternating series theorem, whereby we will have, let me call our Bn to be equals to 1 over n natural log of n to the power of n. And we check the 3 conditions as we did in number 1. The first one is that this Bn is positive because n equals to 2. And we know the domain of Ln. So we will have that this function will be positive because our n is starting from 2. If n was to start from 0 onwards, then from 0 to 1, then the answer could have been affected because ln of n it's a negative. But in this case, our domain is from 2 our domain is from 2 to infinity. So that means that this function is positive. The other one is that now if we check to show that that function is decreasing, we can have our Bn, we can use in terms of x's, f of x, and we have this as 1 divided by x, ln of x to the power of x. So which is the same as writing it like this, x ln of x to the power of minus x. And we can use we can differentiate this one using logarithmic differentiation to get a derivative. So we can have that if we call this y equals to minus x, or sorry, x ln of x to the power of minus x, we can have that natural log of y equals to minus x natural log of x ln of x. And then the derivative on both sides, we have this is 1 over y prime. So this is y prime over y equals to the derivative of this. We use product rule. So we can have minus for the first part, fixing all what is in the other part, x ln of x. then minus x derivative of ln, and this one I can call it u. So derivative, I have minus x. Derivative of this, it's ln of u is 1 over u. So I'll be having minus that one, then u here, then I multiply here by derivative of u, again product rule. So you have 1 with an ln of x, then you add to 1 because of derivative of ln of x is 1 over x, so add 1. So this will become, if I factor out a minus, I will have ln of x, ln of x, then plus x ln of x plus 1, and then the u here, it's x ln of x. And this is y prime over y. And then if you multiply by y on both sides, you find that y prime equals to all what is inside here multiplied by y. And the y function was x ln of x power minus x. So this function is decreasing because it's negative already. So finally, the last part we do here is now we find the limit as n approaches infinity of bn. And we do this, if we find this limit as n approaches infinity, and our bn, it's 1 over n, ln of n to the n. And we observe that this one, as n grows bigger and bigger, this one will go to 0, or we can use the p series. And then we compare the 1 over n ln of n to the power of n with 1 over n to the power of n. And you observe that 1 over n to the power of n, and n is already starting from 2, that one converges. And that one is bigger than 1 over n ln of n to the power of n. So this function will converge. And if you have to do the, that's the absolute, if you have to do the absolute term, again, we find that this function also converges. And that means that this function will converge absolutely, because even we have checked using authentic series theorem with a minus. And also if you have to do the absolute value of this function without a minus, again, it would have converged again. So this thing converges absolutely. That's the end of the session.